So after spending some time on data structures, we have looked at the union find data structure for disjoint set. We have seen heaps, how to maintain priority queues in heaps. We have seen balanced binary search trees. Now let's get back to algorithms per se and try to understand some general strategies that are there for designing algorithms. So one of the tempting strategies for designing an algorithm is what is called a greedy strategy. So let's look at greedy algorithms, some examples of them, and see what it is that we need to show in order to justify a greedy algorithm. So first of all, what is a greedy algorithm per se? So usually we are computing some kind of a global quantity. Right? So we want to find out, for instance, a minimum cost spanning tree. So among all the trees that you can draw on a graph, you want to find the one that has a minimum cost. In order to build this tree, we have to add edges at step by step. So we need to decide whether to add an edge or not to add an edge to construct this tree. So we need to make a choice as to whether to keep an edge in the tree or not use it in the tree. So that is a local choice. So you need to make a sequence of choices such that the overall outcome that you get is optimum with respect to whatever it is you are looking for. So what a greedy strategy does is it makes this choice, this next choice, based on some local property. It says, oh, this is the smallest thing I can see right now, or this is the closest thing I can see right now, so let me add it. And it will never go back and revisit this choice. Right? So it's never going to go back and say, oh, the smallest thing that I chose then didn't work, maybe I should go back and check the second smallest thing, maybe that will give me a better one. Right? So a greedy algorithm will only go forwards. It will pick up something which looks good now, put it into its solution, and never go back and change that solution. So if you don't do that, I mean, if you actually go back and change, then you follow some strategy to find a solution, you say this is not good enough, then you'll go back and you'll find another strategy, then you go back and find another strategy. This is called backtracking, right? So you keep going back and searching through various possibilities, and somewhere, somehow you stumble upon the correct algorithm. So you have to search through a number of possibilities to find the optimum, but a greedy strategy, has this very local way of saying, okay, at this point go this way, at this point go this way. So it just follows one path through your state space and finds the optimum solution. So this drastically reduces how many solutions you have to evaluate for optimality, and therefore it makes the algorithms very efficient. But the real problem is that when you have such a greedy strategy, you have to justify the fact that you are never going to go back and relook at something which you have chosen before. Right? How do you know when you pick up something which seems to be good now that this is going to be the best choice you've ever made? Right? So just imagine, right, that you are trying to buy something. Supposing you're trying to buy a phone, right, and today the price seems to be low. Now, the strategy that you might want to do is say that, okay, if this is the lowest price I've seen so far, I should use it. But what if tomorrow there is a discount offered and then you will regret, right? So a greedy strategy is kind of in that same situation, that it sees something which is good and it says, okay, let's take it. But there is no guarantee in general that something better will not come later on. Or put it another way, you buy this cheap phone and then tomorrow it breaks down. So if you had paid a little bit more and got a slightly better phone, then the phone would have lasted a lot longer. So in the long run, you would have paid less. So this is the difference between, in real life, a greedy strategy and a strategy which looks ahead a little bit to see the consequences of what will happen. So a greedy strategy does not look ahead. So we have seen several examples already of greedy strategies. So the first example was our shortest path algorithm due to Dijkstra. So we started at a source vertex and we tried to find the shortest path to every other vertex. And what we did was we maintained this collection of visited vertices and we kept incrementally keeping track of the shortest distance to every unvisited vertex from this set. And we said that whenever we find now the shortest unvisited vertex, we will add that to this set and freeze its distance once and for all. We say that now there is no better way of getting to that vertex. Right? So the global property that we want is that we want the shortest distance to every vertex from the start vertex that we began with. And the greedy strategy is to locally pick the next unvisited vertex whose distance is currently the smallest. And we showed that because we don't have negative edges, you cannot find a better path later on. So we proved it actually. Right? So for Dijkstra's algorithm, we actually proved that this works. Another algorithm which was greedy was Prim's minimum cost spanning tree thing. It was very similar to Dijkstra in spirit. You grow this tree, which is like the visited set in Dijkstra, and you add a new node to the tree which is connected by the shortest edge among all the other unvisited nodes. So you add a new node to the tree, and then we use that separator lemma to show that the edge that we are using must be in the spanning tree, because it is something which connects this set to that set. It's a separator edge which connects two partitions of your vertex set. But again, we needed a proof. Okay, so we have a strategy. So, but why does this give us a minimum cost spanning tree overall? Because the separator lemma guarantees that whenever we pick up an edge in this greedy strategy, it actually belongs to the spanning tree. And the same is true in Kruskal's algorithm. That is also a greedy strategy. We have a bunch of edges which we have not used so far. We pick the smallest one which does not conflict what we are doing. It does not create a cycle in the tree. Again, the reason it works is because of the separator lemma, but otherwise there is no guarantee that picking up the smallest edge now does not create a problem later on. So in all these greedy algorithms, we explicitly proved that the algorithm strategy was correct, that what it produced was something which achieved the global optimum value, the shortest path or the minimum cost spanning tree that we were looking for. So what we are going to do now is look at other examples and argue why it is not trivial to do this. I mean, why you need to actually show that the greedy strategy that you have picked is a good one, and we will look at some approaches to show that. Right? So let us look at this problem. So suppose, like I am sitting now, there is a special classroom in which one can record these lectures, right. So a number of people want to do this. So different teachers need to use this classroom, but suppose there is only one. So each teacher has a particular time when they are ready and willing to record, right. So they have certain preferences or slots. So every instructor has a preference saying, I want to record from 2 o'clock to 5 o'clock on a Thursday afternoon. Another person will say, I want to record from 11 o'clock to 1 o'clock on a Friday morning. Right? Now these two are fine, but somebody else wants to record from 9 o'clock to 12 o'clock on a Friday morning, then 9 to 12 and 11 to 1 are not compatible. So you might have slots chosen by the instructors which overlap, so you may not be able to honor all the requests for booking. So now if we have next week's bookings available to us, then the question is, how many instructors can be allotted their chosen slots so that we maximize the number of happy instructors. So you want to choose a number of subset of the bookings such that these don't overlap, and if I collect together all the bookings which are actually honored, this set is as large as possible, right. So this is the property that's the global optimum. I want to choose a subset of compatible bookings of largest size. Okay, compatible means that no two bookings in this set overlap in time, so it doesn't require two people to be using the studio at the same time. So since we are discussing greedy strategies, what we will do is we will try to build up this set of allotted bookings one by one. Right? So eventually we want a collection of bookings saying these are all the bookings which are granted for next week, but you must start somewhere. So you must pick up a booking according to some local strategy. You may say, I like this booking because it is a small slot, or I like this booking because it overlaps with very few slots. So there might be many reasons why you think a particular booking is a good one to pick first. Right? So you pick the next booking to allot based on a local strategy. Now because you have picked this booking, just like in Kruskal's algorithm, because you picked an edge, certain other edges now are going to be not useful anymore because they will create cycles. So here what will happen is you pick a booking, every booking which overlaps with this is now ruled out because you can no longer allot those slots. Right? So you will eliminate some bookings from your option, and then you will keep going like this. Now you will pick the next booking which survives this pruning process and say, okay, now I have got a second booking which I can add to my set. Now you will remove everything which is incompatible with that, and finally you will get a sequence of bookings. And when you have run out of bookings that you can add, all bookings are in conflict with some booking you have taken, you will say this is the final answer. The question is, why is the final answer that I have produced now the correct one? So let's see what we could choose as this local strategy, right? The next booking to allot, and see why it is not such an obvious thing to choose one which is correct. So let's start with a very trivial strategy. So I pick up the first booking in terms of time. So the person who has asked for a Monday morning 8 o'clock slot, I just give them the booking because this is the first come first serve, right? So they are the ones who asked for it earliest, not that they made the booking earliest, but they required the studio earliest in the week, so I give it to them. So would this be a sound strategy? Well, one way to show that it's not sound is to produce a situation where this will not give you the correct answer. So here is a situation, right? So here time is going from left to right, right? So let's just assume that we are keeping a calendar and we are just keeping time from left to right, Monday to Sunday or whatever it is. So now the green lines are the intervals that the booking occupy. So this is called interval scheduling. Each request spans an interval, and if two intervals overlap, they are incompatible. So now the earliest booking unfortunately happens to be a very long one, right? It takes the entire week. And my goal is not to maximize the usage of the studio in terms of hours. So that's also important, right? It's important to know what it is you're trying to optimize. So I'm not trying to maximize the amount of time the studio is being used. I am trying to optimize the happiness of my teachers, right? I want to keep as many instructors happy as possible. So I want the maximum number of people to get the slot that they asked for, even if there are gaps in between where the studio is not being used. So in this case, it is clear that it is best to give these 5 non-overlapping slots of choice rather than give this one long slot of choice, but this one long slot is the earliest slot. So strategy 1 fails because you could have a situation like this, right? So this is the type of analysis that you need to do. You have to come up, so it looks like a plausible strategy, maybe not a very clever one, but you have to say why this strategy is not going to work, or if it does work, you have to say why it does work. So here is another strategy. So maybe starting earliest is not a good idea, but surely it is a sound strategy to pick small slots. So if I take a small slot and allot it, then it will leave a lot of time free for other slots, right? So can I take the smallest slot? So if somebody wants to record only for 20 minutes. So can I say, okay, you can go ahead and take it 20 minutes, because if you use it only for 20 minutes, then you're less likely to interfere with the other people's slots, right? So it seems plausible when you think of it that way. But this also doesn't work, because you could have an example like this, right? So you could have 2 long slots and you could have 1 small slot which unfortunately overlaps with both of these. So if I now allot it to the shortest slot, I will rule out 2 slots. So only 1 teacher will get a chance to use the recording studio, whereas if I had not used this strategy but given it to the 2 longer slots, I would have got 2 people using it, right? So remember, the criterion is the number of slots allotted and not necessarily the time duration for which the studio is in use. So this is also not a good strategy. So let's look at a third strategy. So when I take a slot, there are various other instructors whose slots intersect with my slot, right? So my slot is incompatible with a number of instructors because they overlap. So what if I pick a slot which is overlapping with the smallest such set? So I pick a slot which is least incompatible in some sense, right? Then again, this seems plausible, right? If I pick something which is least incompatible, it will reduce the pool by the minimum amount. Remember what happens? I pick a slot, and then once I pick that slot, every slot which is overlapping with it has to be thrown out. So if I pick one which throws out the least number of other slots, then maybe I'm in good shape, right? So this requires a slightly more complicated example to describe, but here is one, right? So in this, if you look at any of this slot, so this is incompatible with all 4 of these, right? So is this. So this is also incompatible with all 4. So all the top row things have 4 things which are incompatible, and these 4 things have themselves, so the 3 others in the same time slot plus the 2 above. So they have 5 things which are incompatible, right? So here I have 4 incompatible things, right? So actually here I have 5, because this is also incompatible there, and here I have 5, right? The 3 which are in the same stack and the 2 above. Whereas this particular slot is only incompatible with 2, the 2 in the middle on the top row. So by this strategy, I would start with this. But if I start with this, then unfortunately what happens is that I have ruled out these 2. Therefore, the only thing I can do is to take one of this left hand side and one of this right hand side. So I can only complete this with 3 recordings. I can take the middle one, and then I can take one from the left hand side, either the top row or the one from the stack, because they are all incompatible. So I end up with a choice of 3. Okay. Whereas if I actually look at the top row, clearly I can achieve 4, but this 4 does not include this slot which had the minimum conflict, right? So choosing the booking that overlaps with the minimum number of other bookings also doesn't work. So what you can see from this is that it is easy to think of greedy strategies which seem plausible and even give an argument as to why this greedy strategy seems like a correct thing to do. But it's a different thing to actually justify that it works. And in some cases, it's easy to say it doesn't work by showing you some situation where it doesn't apply. In some cases, you have to come up with a little bit more thought to come up with a situation where it doesn't apply. So by no means is it obvious that a greedy strategy will work. And in most situations, unfortunately, greedy strategies don't do a good job. So here is a fourth strategy, right? So we started with the strategy which says, let's choose one whose starting time is earliest. So here is a dual one, okay? It doesn't sound very promising because it looks very similar, but let's start with a booking whose finish time is the earliest. So can we come up with a counterexample, right? So supposing you potter around like we have done for some time, it's difficult to come up with a counterexample maybe. So either you have to come up with a counterexample, right? Counterexample, or if you are convinced that this is actually the correct strategy, then you must prove to me that it's correct, right? So it turns out that this is actually a correct strategy. So this particular strategy of not choosing the starting time that is earliest, but choosing the finishing time that it is earliest is actually a good strategy for doing this, right? But how do you prove that it's correct? That's what we are going to argue. So first let's describe this strategy more formally, right? So I have a collection of bookings. Remember, each booking has a starting time and a finishing time. So I have a collection of bookings, and from these bookings I want to construct a subset of bookings which are mutually compatible. They don't overlap with each other such that this subset is as large as possible. So I start with that, and I have a new set which I am going to pull out from the set B of accepted bookings, right? So initially I have no accepted bookings. Everything is in this booking set, that is bookings which have yet to be processed, and A has the ones which have been accepted. So initially A is empty. So at any given point in a greedy strategy says among all the available bookings, now the available bookings by assumption are not conflicting with any booking I have already chosen, right? So among all the available bookings, if there is at least one, so it's not empty, pick the one with the earliest finishing time. So you pick a small b in that set, the earliest finishing time, and add it, and that's the greediness. I just pick it up. I don't have any second thoughts about it. I just pick. Of course, if there are multiple ones the same finishing time, you have to choose one, but you just pick one with the smallest finishing time and put it in, and now you have to prune. Everything which is in conflict with the small b has to be removed because we cannot honor those anymore. So you have to remove from capital B every booking which overlaps with small b. Right? So this is the algorithm. It's very straightforward. So let's see how it works. Okay, so supposing I have these bookings 1 to 9, right? So you can see that again time is going from left to right. So this is the direction of time. So the earliest booking in all these that ends is 1, right? So 1 is the booking that whose time slot ends the earliest. So 1, 2 and 6 all start roughly together, but one certainly ends earlier than others. So I add 1 to my set A, right? And in the process, these two get removed because they overlap with 1. Right? None of the other bookings overlaps with 1 directly, but these two bookings I cannot honor because they would require the studio at the same time as booking 1. Okay, so now these dashed lines are the ones which are ruled out. So among the remaining things, it is clear that 3 is the next one which should be chosen because it is the smallest finishing time among the unprocessed. So the black solid lines are those which are still in capital B, right? The green one, so this is A, right? The green ones are in A, and the dashed lines are the ones which have been eliminated from B because they conflict with something in A. So I choose 3, and in the process of choosing 3, 4 gets ruled out because 4 overlaps with 3, but 5, 7, 8 and 9 are okay. Now I look at this, and then the next thing I choose is 7, right? Because 7 finishes before 5. So I choose 7, and in the process 5 gets ruled out, and finally if you look carefully 8 finishes before 9, so I choose 8. Right? So this is how the algorithm works. It looks among all the remaining ones which one has the earliest finishing time, picks it up, and then rules out everything else. Right? So this is the greedy algorithm, and what we want to argue now first is how to show that this actually produces the largest subset of compatible jobs. Right? So we saw that the algorithm takes a set of bookings B and it produces a solution A by following this greedy strategy, but why is this optimal? So you have to do something to prove this. So when we looked at Dijkstra's algorithm or Prim's algorithm, we looked at the problem we were studying and we said, okay, in the context of this problem, there is a lemma or there is something which shows that a later thing cannot change anything. So like that, we have to come up with a strategy. So here, we are not going to come up with any fix because we don't really have any handle on this problem. So let us just say, let us look at some optimal solution, right? So let's say that there is a different solution which somebody else has produced through whatever algorithm which I don't know, and the claim is that that is optimal. So there is a capital O which is a optimal set of bookings, and I have a set of bookings A. Now the first thing to note is that I am not claiming that A and O are the same, right? Very obviously, I could have, for instance, a situation where I have bookings like this, right? So supposing these are my bookings, then it could be that my algorithm, because it's the early finishing algorithm, picks these two, right? And the optimal algorithm picks these two. But you can see that there is no way to pick more than two. So the optimality is in the number, but it's not in the choice of which slots are honored. So remember, we are not looking at other constraints like, whether the thing is used for a longer time or not. So for instance, I could have a situation where I have two really long slots, right, and two really short slots. Now my algorithm, the algorithm A that we described, will pick this one because it finishes first, throw out this one, then it will pick this one and throw out this one. So it will pick two, but it will pick two which use the studio for a very short time, and perhaps O instead picks this one and this one. So in a sense, O is done better because it's using the studio for more, but it doesn't matter because we are only counting the size. So what we really want to argue is that the size of A as a set and the size of O as a set are the same, right? So we are just saying that the same number of people, may not be the same people, but the same number of people are being satisfied. So to do this, we will first, to prove that this is true, that the size of A and the size of O are the same, we will just reorganize A and O to be a little bit more structured than they are. So remember that each job has a starting time and a finishing time. So obviously the starting time of a job must be before its finishing time, otherwise it doesn't make sense, right? I cannot have a slot that starts at 3 o'clock in the afternoon and finishes at 2 o'clock in the afternoon. So every starting time must be before the corresponding finishing time of that job. But since these are compatible in A, we know that all these things are disjoint. So I can order them in time, right? So I can pick a sequence in which to enumerate them such that the finishing time of the first job is before the starting time of the second job, and the finishing time of the second job is before the starting time of the third job. So I am just ordering them in time, right? So the first job finishes, then the second job finishes, then the third job finishes, and I know that they don't conflict because otherwise they would not be in my solution. And I can do the same thing for this so-called optimal set which somebody has produced. That also I can order in the same sequence. I can say that J1 is before J2 in time, J2 is before J3, and the claim is that I have produced K, but the optimal solution has produced M, and if it is optimal and I am not optimal with my algorithm, then M must be bigger than K. So my goal is to show that K and M are the same, right? So we want to show that K is equal to M. That will prove that the two sets are of the same size. So the way we will show this is to use this sequence to argue that at every point in the sequence, in time, the solution produced by A is ahead of the solution produced by O in time, right? So it's ahead in time. So what I mean by that is that if I look at the corresponding job, if I look at I1 and J1, and if I look at I2 and J2, right? For each job in the sequence, if I look at that Lth job, then the Lth job in my set, in the A set, finishes earlier than the Lth job in the O set, equal to or earlier, right? So f of IL should be less than equal to, remember f is the finish time. The finish time of the Lth job in the accepted set is less than or equal to the finish time of the Lth job in the so-called optimal set, right? So why is this true? Well, we will prove it by induction, by L equal to 1 and so on. So for the first job, remember that what our algorithm does is it starts with the pool of all jobs and it picks the job which ends the earliest globally, right. So, by definition I1, the algorithm the set capital A consists of the first job which ends globally before every other job. So, the set O cannot have a job which starts and finishes earlier than that, right. So, therefore, I1 cannot finish later than J1. So, initially it is true. Now, let us see what happens inductively. So, we are doing it inductively. So, we are assuming that we have come up to some point, up to some L minus 1, and so far we have proved it. Every step the job on top finishes before the job at the bottom. And now we have to argue that it also holds for the current job number L, right. So, why is this, right? So, we want to show that f of IL is less than or equal to f of JL. Okay. So, remember that at the previous step we already knew this, right. F of I of L minus 1 by induction, okay. So, this is induction. F of I of L minus 1 was already smaller than f of J of L minus 1, and this is because B is sorted. Right. So, since B is sorted, I know that the next job that is in B starts after the previous job ends, right. So, the starting point of so this should be, sorry, this is J sub L, right. So, the starting point of the Lth job in the J sequence is after the finishing point of the L minus 0.1 in the J. So, the first inequality is because my induction shows me that the A sequence is ahead of the B sequence at L minus 1, and the second inequality says that the B sequence is sorted. So, the Lth job must start only after the L minus 1 job is finished. From this it follows that f of I L minus 1 is less than S of Fj, right, because I have this two inequalities, right. So, therefore, if this was actually going to be smaller, right, so the job J is compatible with my thing, because f of I of L minus 1, so remember this is S of J of L, right. The L minus 1 job which I have put in set A finishes before this job that the optimum one picks. So, if that job was available to me, it is available to me, and if it finished before IL, I would have picked it, because my strategy says pick the one which finishes earliest, right. So, if f of JL is actually strictly smaller than f of IL, then the greedy strategy would have picked JL. So, if you are claiming that it did not pick JL, then it must be that IL is smaller than or equal to, right. So, that is the proof. So, therefore, if I have already got this greedy strategy maintaining its lead in some sense, finishing before the optimal strategy up to L minus 1, it still stays ahead one more step. Okay, so far so good. So, then what? So, now we still have to justify that K is equal to M, right. What we have shown is that at every stage we are no later in time when we have finished that many jobs in A than we are in O. So, why does this guarantee that I have no more jobs in O than in M, in A? So, supposing it is not the case. So, supposing I have more jobs, strictly more jobs in M than in A, right. So, when I finish at IK and I am at JK, right, at this point I know that this is smaller than this, right. This is what we have proved. Now, if this next job is there, right, and I am not going to add it, it means that at this point I have run out of jobs to add. So, everything else is incompatible with the set I have picked. So, no more jobs remain, that is why I stopped at IK. But the job that is remaining is not incompatible, because for the same reason we know that IK is smaller than JK in the finish time, but JK is smaller than JK plus 1 in the start time, right. So, the next request which comes after that in O is not finished. So, this means that B is not finished at that time. So, therefore, our assumption that B is empty and we stopped is wrong. So, we could not have stopped at K because B became empty. So, we must be able to add K plus 1. So, if M is strictly bigger than K, then there is something wrong with our assumption, and therefore, M cannot be strictly bigger than K, right. So, this is this proof by contradiction. You assume something and you show that it leads to some absurdity, and because that absurdity is not possible, the original thing must have been wrong. So, it cannot be that therefore, this is not a valid assumption. Okay, so m cannot be bigger than k, so it can be at most k. Since you claimed that O was optimal and I claim that I have produced k, then m must be equal to k. So implementing this algorithm, like many greedy algorithms, implementing it is not very hard, right? So what I need to do first of all is to be able to look up the next job by finishing time. So I need to do a sort. So in n log n time, I need to take the set of bookings which are given in capital B and sort them by finishing time. And now for convenience, I will sort them and renumber them. So the first job now, job 1 in my sequence will be the one that finishes first, job 2 second, and so on, right? So the starting times may be jumbled up, but the finishing times are in sequence. So I will now keep the start and finish time for easy lookup. So I will say capital S of I is a dictionary which tells me the starting time of request I, F of I is the finish time of request I. So now I pick up the first booking, and what I will do is I know its finishing time, so I can now go ahead. Okay, so all the jobs to my right finish later than this, but I need to find one which starts later than this, right? So since they are ordered by finishing time, I am going to be processing them in earliest finishing time, but I need the earliest job which finishes after this but which starts after this, right? So in general, after adding booking j, I need to go to the right and find the smallest r such that, of course, it will finish later than this because I am doing it in order of finish time, but it must also be compatible. So its starting time must be bigger than my finishing time, right? So I go to the right, so I will skip over everything between j and r. Then after looking at r, I will skip over it, so I am not going to go back because everything before that is already ruled out because it is already overlapping with something. So I go from r and I look for the next r prime, which is to the right of r prime, which starts after r ends, and so on. So this is a single scan. I need to only go through the jobs in one pass, right? I start with the first one, it will cancel out a bunch of jobs, and I will find the first job which is not cancelled, which can be started after this job ends. And because it is in order of finish time, this will be the earliest finish time among all compatible jobs. And then I keep going, right? So this is the implementation. So it's going to be an order n log n sort plus a linear scan. Okay, so it's a very efficient algorithm. So what we have seen is that this notion of a greedy algorithm is one which makes a lot of choices locally. It looks at the current situation and says this looks best right now in order to achieve something which is globally going to be optimum, right? So we pick the shortest edge now or the shortest distance now in Dijkstra. In this case, we pick the shortest finish time among those things which are remaining right now, such that globally we were going to achieve the maximum number of jobs which are satisfied, or we are going to globally achieve the minimum cost spanning tree or whatever. So in order to do this correctly, right, we have to make sure that this not going back and revisiting a choice is actually correct. So since the algorithm never goes back and revisits a choice, it's very efficient, right, because it only follows one trajectory. So it's going to be a very simple algorithm like the one we saw here, which is actually n log n to sort and then a scan. But we need to show that this strategy is optimal, that we know we don't go back, and because we don't go back, we are never going to reconsider, so that we have always made the correct choice, right? So, and in many straightforward problems like this interval scheduling thing, the problem is that there are many things which look naturally greedy, right? So greedy strategies are not difficult to think of and to informally justify. So we have to somehow make sure that these greedy strategies that we come up with are not wrong, right? So we already saw that the first 3 greedy strategies we came up with for interval scheduling, we could come up with counterexamples. So most greedy strategies are wrong. So when you pick up a greedy strategy, if you are following a greedy strategy to solve a problem, you need to provide a proof that what you are doing is actually optimal. Otherwise, it's suspect, right? So every greedy strategy needs a proof. So just keep that in mind. So we saw in this particular case one way to prove this, which is to show that step by step, if I just examine the order in which things are taken, step by step the greedy solution stays ahead of the optimal solution, right? So there are many different ways to prove greedy things, and there is no uniform strategy, unfortunately, but we can just look at a number of examples to come up with different ways of proving it. So this is one particular solution which says that I can take an optimal solution and I can kind of incrementally show that my solution is never worse than that. Later we will see other examples where we can take an optimal solution and rearrange it to be the same as the actual solution that we get, right? So that will be a different way of proving it.